Good evening, ladies and gentlemen. Welcome to the 8th year of the Goodman Public Forum. So we're starting, this is our first evening of a series of 4 evenings. The thematic of this year is Understanding Cancer Research and Current Treatments, Empowerment Through Knowledge. Bonsoir, mesdames et messieurs, bienvenue à l'Université McGill pour la 8e année des forums publics du Centre de cancérologie Goodman. La thématique de cette année se veut comprendre la recherche et les traitements actuels du cancer, le savoir au service des patients. For those of you who don't know me, I'm Nicole Beauchemin. I'm a rather senior professor in the Goodman Cancer Center. I've been moderating these forums for a number of years now, and I've had the pleasure to work on this with Dr. Peter Siegel, who is sitting right there, and Stephanie Malley, who is walking around upstairs. And we've had a great collaboration from a good number of our colleagues within the center, but also from our colleagues within other institutions or hospitals around Montreal to present a number of topics to you. Before we go into tonight's event, we wanted to take a few minutes to let you know about something pretty serious that's happening. It's been happening for the last 10 to 12 years, and this time we really need your help in terms of researchers, but to help Canadian research altogether. Practically now, the funding situation in research altogether and in cancer research is essentially flat-leveled, if not decreasing. You can see in the graphs that I have up there that if you compare the funding in Canada, which is in red in the left graph, to some of the other medium-sized countries, everybody else seems to be going up in the last 10 years, but we have been essentially going down. And on the right panel, if you look at the arrow, the red arrow going down, this is the amount of money per researcher. So in the last 10 years, the amount of money has been systematically going down. Pretty much everyone knows this, but to quantify it and to make it believable and to make it scientific, there was a panel that was set up by the government, and the director of this panel was Dr. Naylor. So the report is now called the Naylor Report. There were a lot of, it's a 175-page document with a lot of information. And in there, it basically says Canada dropped out of the top 30 nations for research intensity. Granting councils were uncoordinated. The issues of diversity and equity and inclusion were not necessarily completely in phase. And particularly the early career researchers were struggling in many fields. So why am I telling you this? Well, with research, we need money. And to get money, we need to convince the federal government that they have to reinvest back into research. And one of the ways that you can help us is by contacting your local MPs and telling them that you support the reinvestment of the Canadian government back into the Canadian science, and preferentially sooner than later. And why are we telling you this now? These decisions are presently being made in Ottawa in various committees in the cabinet. They're now discussing the spring budget. How much money did the Naylor Report recommend? They recommended an increase of $1.3 billion over the next 4 years. And what this would do, it would bring us back to the level of 2007. So it's not asking for all that much money. It looks like a lot of money, but within the time frame and within the capabilities of the federal government, it is certainly something that is doable. And the only way that this will actually be implemented is if the public has our support. You might have seen during the summer in the newspapers, on the internet, at the television, that a lot of researchers have been promoting this event, have been promoting this idea. So if you care about science, if you care about medical research science, if you care about medical treatments for the cancer patients, take a few minutes and write them and tell them that this is important. Maybe they will listen. I'm not promising anything, but maybe. This year, we will have 4 lectures. The first one tonight, as you know, is on ovarian cancer. We have another one on November 29th, which is a totally new topic, and it's going to have to do with cancer pain management. This is an important issue, and we've never actually proposed this topic, and I think it should be interesting to anyone who has gone through the ordeal or has family members that have gone through this, so you might be interested in coming. And then we have 2 other events. One will be on brain cancer on April 11th, and the last one, there's been a lot of talk about stem cells and cancer stem cells. We're going to try and unravel it for you, and this will be on May 16th, when spring is back. Tonight, we have the pleasure of hosting some of our friends from the SHUM and from the Jewish General Hospital and from, of course, the Goodman Cancer Research Center on ovarian cancer, the latest developments in targeted therapeutics and screening methods. Our first speaker is Dr. Walter Gottlieb. Dr. Gottlieb is a professor of obstetric and gynecology, and he's also a professor in oncology at McGill University. He's the director of gynecologic oncology at the Jewish General Hospital and the director of the surgical oncology at McGill. He obtained his medical degree summa cum laude, which means the top highest grade that you can have at the Université Libre de Bruxelles. He is a native of Belgium. And then he went on for board certification in OBGYN. He then moved over to the NIH, where he obtained National Cancer Institute Award of Outstanding Performance. Then he performed a 3-year fellowship in gynecological oncology at UCLA. Then he moved to Tel Aviv for a number of years, where he co-founded and built the Department of Gynecology and Oncology from 1994 to 2003. We were lucky enough at McGill to recruit him to McGill, and he is essentially now been performing his clinical duties and involved in scientific research in ovarian cancer as a project director at the Lady Davis Research Institute. Those of you that might remember, he presented to us 5 years ago and told us this incredible story on the pioneered and driven robotic surgery, which is making all the difference for patients in gynecologic cancer in Canada. He's published over 150 peer-reviewed manuscripts. He's the director, the vice president, the president of a number of agencies, both in Canada and internationally. So it's my great pleasure to welcome Dr. Walter Gottlieb. So for all the presenters tonight, as you can see, there's this really shining light in our eyes. We are being taped, which is good for everyone. The videos will actually be uploaded on our website within 2 weeks. What it also means, it limits your movements to the camera. Thank you.
As long as you put your makeup on, you're okay.
Okay. Good evening. Thank you very much. It's a real pleasure to be back here, and welcome everybody. So tonight we're going to be talking about precision medicine and how this really has affected ovarian cancer. when we look historically for 2,000, 3,000, 4,000 years, medicine was practiced based on that intuitive sense of, the doctor had kind of an impression, he would taste the urine, it was sugary, and then in the 50s, 60s, that started to change, and we started to go into what we call evidence-based medicine. And evidence-based medicine is when you put, big international studies comparing 1,000 people with one drug versus 1,000 people with another drug, and you try to compare which one is the best. And that is slowly fading away and giving way to what we call the precision medicine, which is basically molecular-based therapy, individualized therapy. And we usually like not to be pushed by the past, but to be driven and pulled by the future. And this is really what this lecture is about, is how is tomorrow going to be? Tomorrow is going to be about creation value in precision medicine. It is the credo that tomorrow it's going to be about where technology cures and caring heals. And this is very different, and there is no other way. And a lot of our colleagues still have it a little bit difficult. There is no other way. We just have to go there. And the real question is what's going to come after the molecular paradigm, but that we don't know. For tonight, we're going to talk about why ovarian cancer is called the silent killer, about some new precision drugs that are available here and now, and about very recent updates. We heard about robotics 5 years ago, but very recent updates actually on robotics in ovarian cancer. So why do we call ovarian cancer the silent killer? Well, ovarian cancer starts in this area. And actually, today it is believed that the ovary is more a fertile ground where cancers can grow than really where they start and they originate. And you can imagine that the cancer starts in this area, deep in the pelvis, in an ovary that's really not innervated. And thank God it's not innervated, because throughout evolution, those who had ovaries that were innervated probably didn't fare very well, because every month with ovulation it would have been a disaster. So the ovary is not innervated. In addition, by the time that somebody develops an ovarian cancer, usually in their 60s, well, the ovaries don't produce any hormones anymore, so that is not a symptom. And it's not a question of fertility. It's not that you won't get babies because you're past that age. So it can develop slowly and grow into the abdominal cavity up to a point where it starts to disturb the neighbors. And that's only when it becomes symptomatic and when people go and seek attention and medical attention. So the question then is, sure, well, intuitive answer is, why don't you screen for it? Well, the short answer is, by the time you screen and you find it, it's too late. And I'll try to show you that. In June of this year, there was a big symposium at the OBGYN conference in Ottawa. And the title of that symposium was Screening for Ovarian Cancer. And you can see we lacked a subtitle. So we were kind of trying to figure out what a good subtitle would be. And these are the subtitles we came up with. Sucks, tilting at windmills, futile, screening NIFs, first do no harm. And then we realized, well, we can't do that. That's not politically correct. So we went down a notch. And we said, doesn't work, why not? Prevention beats screening, the good, the bad, and the useless. And we felt that's still not completely correct. So we went back down another notch to be politically correct. And is there any value? Where are we now? Highs and lows, good news, and you kind of see. Until ultimately, we found the subtitle. And we took the guru of politically correctness, and that's the title we came up with. So this to say, this is in order for you not to forget it. it simply does not work. And I'll show you the evidence why in just a few slides. So we're going back to that lady, and she has a 1 centimeter here that you could see, just a little dot of 1 centimeter tumor in the ovary. Now 1 centimeter is early. Nobody would argue that that's, something like that down there, really early. Now 1 centimeter tumor represents 1 gram of tumor. And 1 gram of tumor is 1 billion cells. Now, in order for 1 cell from where the cancer starts to become 1 billion cells, it has to undergo 30 cell divisions. 1 to 2, 2 to 4, 4 to 8, 30 times in order to get to 1 billion cell, 1 centimeter. Now, for that tumor to become 8 centimeters, nobody would argue that an 8 centimeter tumor is not an early cancer, is basically 3 more cell divisions, from 1 to 2 centimeters, from 2 to 4, and from 4 to 8 centimeters. So the vast majority of its life, that cancer has passed to just become 1 centimeter. 90% of its life, it has passed to become just 1 centimeter. Only 10% to become 8. Where do you think that cancer has learned to be aggressive? Where did that cancer develop most of its life? Before it became 1 centimeter. So the notion, the whole notion of early cancer is a vision that we want to believe in, but that really doesn't exist. Because by the time it's early, it's already extremely late in the pathway of that cancer. In 2013, a great colleague of ours, Laura Elliott, who is in London, basically took all the studies that were available, 10 big randomized studies back in 2013 from various sources all over the world, and she did an analysis on them, a meta-analysis. Her conclusion, which is all of our conclusion also, screening did not reduce mortality in general. Mortality due to ovarian cancer wasn't reduced, and screening did not diagnose the cancers at an earlier stage. That's out of 10 big international studies. However, what it did increase is the number of surgeries done for non-cancerous conditions. And with that came the complications of surgery, which was about 15%, 6% of them serious. So screening really not only didn't it help, but it actually harmed patients. So that was in 2013. In 2015, there was a large study that we all waited for in the United Kingdom with 200,000 patients. It cost 25 billion pounds, I think, if I remember correctly. And when we analyzed that data that was published in December 2015, the Society of Gynecologic Oncology of Canada came out with this. There is no statistical difference in number of women who succumb to ovarian cancer between control and study patients. That means screened or not screened. There was an increase in intervention in the screened women with resulting morbidity, which we knew since 2013. The routine screening cannot be recommended at this time. That came out in January 2016. In September 2016, the FDA woke up and they recommends against using screening tests for ovarian cancer screening, FDA safety communication. So clearly, screening doesn't work. So what does work? Obviously, I'm a very optimistic person, so there must be something good in this. Well, what does work is risk-reducing surgery. And prophylactic salpingo oophorectomy is close to 100% effective, 97% effective in decreasing the risk of ovarian cancer. This is a lecture on itself, and I'm happy to come back in a few years to share that with you. But so basically the take-home message is screening early detection does not work. If you want to prevent it, you can do risk-reducing surgery. Let's go over to the next part of the presentation, precision drugs. So until recently, the way to treat ovarian cancer was one size fits all. You had a cancer on the ovary, you would get the same chemo, and we wouldn't give it a second thought. We then learned, and you'll hear a little bit later from our next speakers, that there are multiple mutations that can be associated as cause, as drivers of ovarian cancer. The interesting part is that about half of those mutations here on your left side are related to defects in repair of DNA. Now, why is that important? Well, it is important because many things cause DNA damage. And it is evaluated that there is 100 with a lot of zeros behind DNA lesions per day in your body. This has led actually to the Nobel Prize in 2015 for 3 scientists that had discovered the mechanisms how your cell repairs DNA, which is a fundamental necessity in order to survive. Let me give you an example that is very relevant to ovarian cancer. This is a DNA brand, and when you have a breach, a single-stranded break, a break in one of the 2 DNA ladders, then there is an enzyme, which is called PARP, that goes and sits on it, and it goes and gets all of what it needs to repair that DNA. If you block PARP, what happens is that all of these other enzymes that are necessary to replace this are not brought in, and you end up with a complete break of the DNA, which is called a double-stranded break. Let's go and see what happens with a double-stranded break. So with that PARP inhibitor, you stopped the repair of the single-stranded, you end up with a double-stranded break, and in a normal cell, because it has what it takes to repair a double-stranded break, the cell survives. In the cancer cells of those patients, those 50% who cannot repair DNA, what happens is the cancer cell dies. So by giving a PARP inhibitor, which is basically an oral medication, you don't affect any of your normal cells, but you selectively kill the cancer cells. These drugs are easy to take, don't cause almost any symptoms, and synthetically lethal, this is how it's called, synthetic lethality, kills the cancer cells and not the normal cell. This has been originally published back in 2005, and it took about 10 years until the Europeans in 2014 approved the drug to be given to ovarian cancer. Very soon after, a month after, the Americans, the FDA in America, licensed it, and within the next 2 years, 2016, 2017, 2 new drugs were approved as inhibitors of PARP to be given for ovarian cancer. So where is Canada? Well, Canada didn't do that bad. Already in May of 2015, 6 months after the Europeans and the Americans, Health Canada approved PARP inhibitors in Canada. Hooray. Almost. So they approved the concept that it is a good drug. But it still needed to be reimbursed by the government. And both PCODER, which is the Canadian agency that decides on reimbursement, as well as INES, which is the Quebec, because we have our own, who decides on reimbursements of these drugs, have refused to reimburse these drugs. They found the data not good enough. 50 countries in the world, it was good enough, including all of the European countries and the United States. For Canada, not good enough. What happened since then? Well, this year, actually last month, PCODER, which is the rest of Canada, approved it. They said, you know what, by the way, we got some more information and we should approve it, like the rest of the world. INES has decided to make their decision in February of 2018. That means that we are in Quebec, Quebec women have a delay of close to 4 years by the time they'll be able to get the drug here. We talked about advocacy. If you write to your MP, just add a little line about that too. I don't know how you feel about it, but I don't feel very good. So the last part is about how robotics has found its way into ovarian cancer. And actually, you could see we submitted our work yesterday to be published. So you're the first one to hear about it. As surgeons, we are licensed to aggress people with a knife. But we need, at the same time, to be extremely careful on how we do this. From a patient's perspective, the value of a surgery is going to be the efficacy of the surgery divided by the invasiveness. If you can provide the same efficacy with less invasiveness, the value for the patient dramatically increases. And this is where laparoscopy originally and robotics really kicks in. So robotics is really not the right word. What it happens is that you have a surgeon who sits at the console here, and he mobilizes these arms, which are laparoscopic arms. So it's not really a robot that operates, right? It's still the surgeon that mobilizes mechanically the instruments. Instead of the hand mobilizing it, it will be the machine that mobilizes the instruments based on what the surgeon does. These instruments are pretty interesting because they have 7 degrees of freedom, which is 2 degrees more than a human hand. So I can't operate like this. The robot can. In addition, these instruments are extremely small, so you're capable of performing very high definition surgery with very little damage to the surrounding tissues. And this is where the rubber hits the road. So in red, this is 100%, in red were the surgeries that we did by open surgery, classical open surgery. And in yellow was what we were doing laparoscopically. So 85% of our patients, grosso modo, received open surgery. About 15% of our patients got laparoscopic surgery. In December 2007, the robot came into our hospital, and look what happens. We started to do way, way, way more minimal invasive surgery, up to the point that for endometrial cancers, uterine sarcomas, and cervical cancer, we reached 97% of patients having their surgery done minimally invasive, meaning that instead of a big scar, and it's kind of interesting, when I trained, I remember a very good surgeon who said, the bigger the scar, the bigger the surgeon. Don't laugh. And however, today, I think that the paradigm has shifted. And the paradigm today is the smaller the scar, the bigger the surgeon, because that's the biggest benefit for the patient. So this was for endometrial cancer, uterine cancers, cervical cancers, and we said, why not ovarian cancer? So this is the same thing, 17%, we went over to 95%. And we realized that the quality of life, this is the quality of life as evaluated by patients, they get an 8 out of 10. You could see that with robotic surgery, it basically didn't change. So there was not that big dip that patients have after open surgery. When we looked at their utilization, this was published 2017, this year earlier, the utilization of pain medication after surgery. In blue is the pain medication for open surgery, in orange for robotic. That's acetaminophen, Tylenol. These are non-steroidals and also morphine. And you could see that patients use almost nothing as pain medication after a robotic surgery compared to what they used after. So pain is much better, which explains part of the quality of life. One important thing, of course, and this is the data on ovary, actually, that's just going to become published, I hope, where this is the survival in patients who had robotics. This is the survival of the historical cohort who had it in open surgery. It's kind of the same. It looks different. It's kind of the same. There are some reasons why robotics might be better, but ultimately what was important here was to show that we did not affect negatively the survival of patients with ovarian cancer by doing it robotically. So at least they have the same survival. They have way less blood loss during surgery. You could see it goes from 500 to 170 or from 400 to 130, which is highly statistically significant. And their hospital stay is way shorter. We went over from, in one group who had chemotherapy before, from 9 days to 2.6 days. In those who didn't have chemotherapy before, from 15 days to 2.6 days, which is very short. And within those who had robotic, within 24 hours, half of our patients went home. And 3/4 went home within 48 hours. So this was extremely effective for allowing women to go back to their families, to their life, to their activities, and to their normality very quickly on. So this is how it kind of looks in a robotic room, and everybody looks at the surgeon sitting nicely at the console, and at, the patient's. But the most important part of this picture is this here, which is a computer. And that computer is between the surgeon and the patient. Now, that computer can do a lot of things. It can do all kinds of digital analysis. This is just for you not to read. It can do a lot of things. It can analyze the color of the tissues, the movement of the tissues, the temperature of the tissues. It can analyze a lot of things that I will show you. And this is some of the papers that we've looked at ourselves. It can, for instance, see nerves that are usually not visible at the time of surgery. It can see structures by using immunofluorescence that are not visible by the naked eye. Here, this is a nephrectomy sample, and what it does is it shows here an overlay of an MRI and a CT scan where it shows you where the tumor is and where the vessels are. So while you're doing the surgery, you have a virtual image showing you how to go between the vessels and get straight to the tumor. It can show you multiple things like Doppler ultrasounds, MRI images, different vision of what you're doing while you're doing your surgery. That computer also, what it can do is you can put in the information in that computer, meaning you can put MRI, CT scan, PET scans, ultrasound images, everything in the computer. And the computer can basically recreate your anatomy. And once it has recreated your anatomy, you can train on the surgery you're going to do the next day, the day before surgery. And you could see all the pitfalls you might get into the day of the surgery. It also allows for teaching at a distance, because the computer can be hooked up in a way that somebody 5,000 kilometers away can see what you're doing both inside the patient and outside and give you advice on what to do. There has even been a surgery that was performed transatlantic, where the surgeon was in the United States and the patient was in Strasbourg. That's kind of the idea of where we're going to. This is not ready for prime time yet because of problems of telecommunication. Telecommunication is not stable and not quick enough to allow this. But as soon as that gets up to speed, that will be possible. So you could have your surgery and you can ask somebody who's the expert on the right upper side of the thyroid to do that part of your surgery, and have the rest of the team be done here. It can also analyze what the surgeon does. So at the end of surgery, we can get a sheet of saying, today you were really lousy, huh? Robotics has been only one company over the last 20 years. And actually 2 weeks ago, a second company came into the market, actually. So we have now, since 2 weeks, 2 companies, which is extremely good for competition and to stimulate them to get even better of what they're doing. Overall, what can we say about robotics? Robotics is basically laparoscopy with a computer between us and the patient. And that computer can do a lot of things. For the moment, what it does, it decreases, we showed, the laparotomy rate, no open surgeries anymore. And that's really the purpose, is to eliminate open surgery. This is not, competition with laparoscopy. If you can do it laparoscopically, the benefit is the same. The issue is giving that opportunity to the majority of patients, and that laparoscopy has not been able to do. Less complications, improved quality of life, less pain, less blood loss. I've shown you that data. Robotics will be the step into precision surgery. Surgery will allow, because of that computer, to do precision surgery, which goes back to what we said about precision drugs, about the whole notion of that new era of personalized medicine. I didn't show you the statistics. So there are a few new games in town, and we need to decide if we're going to play ball. This is a wonderful machine. This is a Spitfire. This is a machine that allowed our parents and grandparents to keep the world free during the Second World War. This is how it looks today. I don't know about you, but if I have to go to war, my decision is taken. And that really doesn't take anything away from the big pioneers in aviation. They were still the big pioneers, but times are moving, and we need to create the future for our children. So, we talked about the silent killer, and that screening doesn't work and only prophylactic surgery does at this point. We talked about a completely new era of precision drugs, and we'll hear more about it. And we talked about how surgery also is getting into the new era of precision medicine. Thank you very much.
So thank you, Dr. Gottlieb. The question period, for those of you who are not used to our evenings, the question period is at the end. We've given you some cue cards and some pencils, so if you have questions, write them on there, and we'll collect them after the last speaker, and we'll have a question period then. Our second speaker tonight is Dr. Anne-Marie Messe-Masson. Anne-Marie trained as a molecular oncologist and obtained her PhD from the Department of Microbiology and Immunology here at McGill, down the hill, in 1984, when we were all young. Anne-Marie joined the Institut du Cancer de Montréal and the Department of Medicine at the University of Montreal in 1989 after a postdoctoral period, if I remember well, in California. Exactly. She became a full professor in 2001, and she's presently the scientific director of the Institut du Cancer, the director of the cancer research at the Centre de Recherche du Centre Hospitalier de l'Université de Montréal, for short, CRCHUM. She's done pioneering work on biobanking, and she's been studying ovarian cancer for a number of years now. She's established a translational research program that's largely focused on delivering personalized medicine in oncology. She focuses on the prediction of therapeutic responses and the development of new therapeutic agents for ovarian cancer. And her title is Getting Personal with Ovarian Cancer, New Avenues to Tailor Treatment. Anne-Marie.
So we're going to switch gears a little bit. We've talked a lot about what happens in the clinic. What I want to talk to you about tonight is what's happening in the research lab, and more particularly in a research laboratory that I direct in collaboration with a gynecologic oncologist, Diane Provencher, and our work on ovarian cancer. So this started back as somebody pointed out a long time ago. When I first came to the Cancer Institute, I used to work on mouse models. And a surgeon who worked on ovarian cancer patients came to see me, and she says, "You have to stop working on your mice. My women are in dire need of help. They're much more interesting. You'll have to focus on them." So I said, okay, but the problem is we don't have a model system. How are we supposed to be working on these women? How are we supposed to be doing basic research when we don't have any tools? So one of the most important things that we could do, or that we did, is actually start to work with the tissues from women who were diagnosed with ovarian cancer. And this is known as a human biorepository, or a biobank. At the time, it was something that wasn't regularly practiced. Now it's become part of, in some cases, even standard of care to bank it. So what it involves is, after we have informed consent from a patient who understands what we want to do, that we actually want to have a piece of her tissue or some blood or some urine that we can store for the next 10, 15, 20, 30, 40 years, as long as it's useful, and do research on it to try to understand the disease better, and then find tools that we can go back to the clinic and hand over for the management of ovarian cancer patients. So the women consent to have us access to their tissues and to their clinical data over time, so we can follow them over the years to see what happened to them. Did the disease progress? Did they respond well to therapy? Did they not? Was it a very aggressive disease? What type of disease it was? So we can do that with the tissues, but the tissues is just a starting point, because you can only do so much with tissues. You get them, it's a piece, it's static in time, and you can look, but you can't really do a lot of biology studies on them. So one of the things you can do is you can take that tissue and actually start to grow it in the lab. So oftentimes what will happen is it'll grow for a little while on these plastic dishes and then it'll die. But every now and then, 1 in 100 times about, it'll actually keep growing and grow and grow, and we can keep it, some of them we've had for 30 years. So these we can study over time, we can manipulate them, we can change the content, we can test new drugs on them and see what happens, so they're very useful. So we've developed 30 cell lines. If you do a calculation, that means we had to try this 3,000 times to get those 30. So that means a big investment over my lifetime of putting, and my students' lifetime, of putting these cells in culture and developing these cell lines. These cells then grow as on 2D plastic, which doesn't look anything like the tumor microenvironment. So one of the things we did is we developed more complex models, what we call 3D models, so they can grow as organoids or spheroids. So now they're starting to look a little bit more like a tumor looks like in vivo. And in some cases, we can return the cell line we go back to that mouse, but this is a mouse that doesn't have an immune system, so it doesn't recognize this as a human cell, it doesn't attack it. So the tumor can grow in a mouse, and we have a preclinical model. And in some cases, we can put that tumor directly in a mouse, and these are called patient-derived xenografts, or PDXs. So those are the model systems that we can work on to study ovarian cancer. So this is just to give you an idea of our recruitment. So in 1990, after having met Diane Blanchet, we actually consented 2 women, got 2 tumors into the biobank. In 2015 is the last numbers that I have, but it continues to grow. We had over 7,000 women that we had consented. That means we have to track their tissues, we have to track what we do with the tissues, we develop cell lines, we develop primary cultures. So this has given us an incredibly rich resource on which we can do our research. And although I can't tell you about all the work that we do in just a short time, what I do want to tell you about is sort of some of the new things that we're trying out. So one of the things that we've been doing for a lot of years is making something we call tissue microarrays to study biomarkers. Those markers that tell us a biological feature of the protein, a piece of DNA, something that tells us something about the patient, how they're going to progress. Are they going to respond to drugs? Are they going to live long? Are they going to recur? So in order to ask those questions, we could take patients one at a time. It would be costly, it would be laborious, and it was hard to do. And we could do these studies one by one. But we have tricks to go a lot faster, and one of them is called a tissue microarray. So in this case, what we do is we take the tissue that comes from a pathology department. So normally after surgery, the pathologist looks at the tumor, cuts it up in little bits, fixes it, and then embeds it in wax. So these are what we call FFPE tissues. We could cut those in small slices and study them one by one patient at a time. Or we can make these tissue microarrays where basically what we do is we have a pathologist look and he says, oh, this is a nice tumor area, you should pick this. And we pick what we call these little carrots. So it's a needle that goes and picks it. And we put it in a new block, which we call a receiver block. And we can take 2 or 3 from the same patient just to make sure that we have a good representation. And we can do this for hundreds of patients. Now when I make a slide and I look at a biomarker, I'm not looking at 1 patient at a time. I can be looking at 100 of patients at the same time. So I can do my research a lot faster now than I could before. So you've heard from Dr. Gottlieb sort of the changing paradigm in terms of cancer care, where, you know, in the 90s it was generic care. It didn't matter what kind of ovarian cancer you had. You came in, you got the same type of treatment. As time goes on, we're starting to stratify care a little bit. We recognize there are different subtypes of ovarian cancer. They shouldn't all be treated the same way. And now we're going towards a much more individualized care. We're saying your tumor is not similar to the tumor of the person beside you, and you shouldn't be getting the same drugs, or you're not going to respond the same way. So we need to tailor the treatment that we give you. So that's our personalized medicine. Why is it so important? Well, it's because when we gave drugs in the old way, where we'd have a group of patients that had ovarian cancer, they would all be lumped together, and we'd have different outcomes. So we could have what we wanted is a drug is beneficial and it's not too toxic and it provides benefit to the patient. But at the same time, we had people who it was beneficial, but there was some toxicity. Worse, we had people where there was no benefit at all, and the worst case scenario is the drug is toxic and you derive no benefit. And we used to give drugs like that to everybody, knowing that only a certain percentage of them would respond well. So the real trick to personalized medicine is saying, how do we separate out those groups, find the ones that are going to benefit from the treatment, and those who don't, let's start focusing on other options. So one of the ways that people classically do this is what we call predictive biomarkers. And predictive biomarkers really is, we want to see something in the tumor that we can assay in a pathology department, and that's going to say, aha, I should be treating you with this and not that. And so one of the ways we do it is we have what we think is a good candidate that is going to predict response. We get antibodies that we know really well. We test it on these tissue microarrays, so hundreds of people at the same time. And then we look, did they respond to therapy? Did they not respond to therapy? Do they live longer, not longer? And that helps us do the work. In breast cancer, you know, for personalized medicine, they hit a home run pretty early. They started with just the ER, the estrogen receptor. It was the first thing that they used to separate out breast cancer, so they knew whether they should treat you with an aromatase inhibitor or not. Then Dennis Slayman in the late 1980s discovered that there was a subset of women that had really, really bad prognosis in terms of their breast cancers. And what he found is that they had an amplification of a certain gene, a receptor at the cell surface that was called HER2 or NU. And they were able to develop therapeutics that were specific for this. And what they could do is in a pathology department now, if you are diagnosed with breast cancer, they will look for the expression of this protein, either looking at the protein by immunohistochemistry or looking at the DNA to see if it's amplified by a technique that's called FISH. And if you're positive, then you will be given Herceptin. And it's changed the course of the disease for these women. They're no longer in the worst prognosis group. In fact, they do rather well. But it's important only to give it to the women who actually have this amplification, because there's a lot of toxicities associated with it, and it's expensive. So you don't want to give it if it's going to be useless, or even worse, if it's going to be toxic. So Walter has talked to you about some of the exciting new developments in ovarian cancer, and one of them is the Parp-inhibitors that are coming online now. As he mentioned, the Parp inhibitor is normally works by creating a synthetic lethal where you start with a single strand break that you can't repair that turns into a double strand break. Now, you may have heard of hereditary forms of breast and ovarian cancer, and they're related to a specific gene called the BRCA1 or the BRCA2 gene. It is the gene that is carried, or the mutation that's carried by Angelina Jolie. That's the mutation, the gene that she has. And in her case, she did prevention, where she did prophylactic oophorectomies, and she also had her breast removed in order not to get breast or ovarian cancer. So this drug was thought to be effective in these women with hereditary cancers because they said they won't be able to repair their DNA, and so unlike the normal cells, they will die. And it worked pretty well. But one of the things that we noticed in the clinical trial was that even if you looked in women who had the mutation, so theoretically, those women should have all responded to the drug. In fact, less than 50% of them responded. So it's a little bit trickier than just knowing one biomarker. It's just not telling us the whole story. The thing is that we looked in women who didn't have the mutation, and actually 25% of them did respond. so we don't know why. And if we just used our marker BRCA1 mutations or BRCA2 mutations, we would be depriving these women of access to PARP, when in fact it might be efficacious. So this is where the story veers a little, and my lab has worked on biomarkers for many years, but in the last 10 years, we decided to bet against ourselves and said, you know, biomarkers are really complicated. There are a lot of DNA repair enzymes. There are a lot of biochemical pathways that are complex. So trying to predict, just by looking at a genome, how a tumor is going to respond is very difficult. It's very tricky. And it doesn't always give us the right answer. So what could we do instead if we didn't want to look at the biomarker? Well, the obvious thing is say, well, let's look how the tumor responds. How could we do that? Well, we've done it in PDXs. We can take it out, we can grow it in a mouse, and we can actually treat the mouse with different therapeutics. The problem is it takes anywhere from 6 months to 12 months to get that answer when things go well. Way too long for the clinic. There's no way that an oncologist is going to wait 6 to 12 months for the laboratory to tell them what you should be treating your patient with. So how could we do this quickly so that we actually get our answer within a 2-week time frame, which would be suitable for the clinic? So how do we test it directly? How do we miniaturize it? So we took advantage of the fact that our hospital is affiliated with an engineering school, and there's a lot of really smart engineers that love to miniaturize everything. So one of the things they've created is called these microfluidic systems, where you can grow or you can hold pieces of tissue in a very small system, and you can actually treat them with drugs. And you can keep them alive. Well, this was the theory when we wrote our first grant 10 years ago. We could keep them alive, we could test them with therapeutics. So this is the overall strategy. So an ovarian cancer patient goes for surgery. We get access to the tissues. We turn this big tissue into these tiny little microdissected tissues. We call them MDTs. So you can see them by eyes, but they're size of a biopsy punch, so there's about 300 millimeters. You load them on these systems, and you can load a lot of them in any one well. And then you can either leave them just growing normally, happily in an incubator, or you can expose them to different drugs, different concentrations, different combinations. And then you can look by different ways and say, are the cells alive, or are they dead? And try to choose your treatment based on how those microdissected tumors actually worked. So I'm really hoping this will work, because it's the first time I've tried a video in a presentation. So this is how your day would go, or your week would go if you're looking at these. Oh no, that didn't work at all. Okay, so as I mentioned, we start off with our informed consent. So we explain to the patients what it is that we want to do. Then after they've consented to them, we register them as participating in our biobank. They go for surgery. Now this is not the robotic surgery, this is an old video that we made, and so we're in the open phase of surgery. After the surgery, once the tissue is removed, then the tissue is taken to pathology. The pathologist takes the piece that he needs for his diagnosis, and then he gives some of the tissue to the laboratory. So what we do is we register it into our log, what we received at the time of surgery, and often at the same time we'll get some of the blood too that'll help us in our studies. The sample is then macrodissected, and in many cases it's frozen away for future research for the biobank. But in the case of the microdissected tumors, we take that tissue, and before we freeze it, we take small little pieces to make these MDTs. So these are small strips of tumor that we've taken, and now we cut them up carefully into these tiny bits. We can still see them. So this is not exactly a precision robotic. This is a graduate student cutting up tissues, which we collect. Then under the microscope, we take these and we punch them now with these biopsy needles. So you get these little discs of tissue that you can get hundreds of these from a tumor. Then we load them on these microfluidic systems, so we draw the tissues into these capillaries, And when they get over the well, the tissue drops down by gravity into these wells, and then we've loaded, these are the channels that are miniaturized with all the tumors in it. Now we can put chemotherapeutics, we can put them in incubators, we can grow them. This is at the end after we've done our experimentation. We can add actually color so that it's easy to follow the tissues afterwards. So they're going to be a little pinkish hue so we can follow them. Then we fix the tissue just like they would do in pathology, so now the cells are no longer alive. We take this device, which is made of 2 layers. The top layer is the channel, which we peel away. And on the bottom layer, you'll see all of these little pink dots. Those are the tissues now that we've taken from the patient. We can now trim this so that it fits into a standard histology cassette. And then we pour, these are fixed tissues. We pour molten wax on top of them. So the wax is going to work its way into all of the little holes within the microfluidic device, and it's going to congeal. Then we can take them out and then put a cassette on. So after that, we're going to be able to manipulate it very much. These look exactly like a block would look in pathology. When we take it out, now we still have that part of the microfluidic device that's there. We can actually peel it away. And when we peel it away because of the wax, now those little tissues are stuck in the wax. They're no longer in the microsystem that we have. We add a little bit of wax on top of it. And then what we find is that after it solidifies, the problem is it's a little bit wavy, you know, the tissue is not at the same height. So we put it back in the oven so that all the tissues can sort of float to the bottom and settle to the same level. Then we let it re-solidify. Now we can process it pretty much like we would do a TMA or even an ordinary block. So this is actually how we trim and how we cut those tissues. It's called a microtome. It gives you these very, very thin slices of wax in which you can see small slices of the tissues that are now available for experimentation. In order to study protein expression, we use the same machine that they use in pathology. This is on the research side. So we have antibodies that recognize our proteins of interest. We allow the machines to run through the different steps in order to be able to visualize it. So you saw those pictures, either the brown pictures or the nice fluorescent pictures after we use different secondary antibodies. And then the tissues after that, when they finish running through this, we just do a final fixation and they're ready for analysis. Whew, I'm so glad it worked. Because it would have been a very silent 4 minutes if it hadn't worked. So actually, when we look at it under the microscope, this is what it looks like. So on this side here, you have the tissues that have been kept in the microfluidic devices for 8 days. Just with regular media, so we haven't done anything to them. We've tried to keep them nicely alive. So this stain, this antibody, when it turns brown, it's because the cells are alive and happy. And this stain, which is a marker for cells that are undergoing apoptosis or dying. So in the controls, you can see the cells look generally healthy. They're dividing and not too much apoptosis. But you see the same sample that was in another channel just beside, where we gave the same therapy that we would give an ovarian cancer patient. You see that actually the tissue doesn't look all that good. There's really not much healthy cells anymore, and a lot of it is dead and dying. And if we look what happened to the patient who got exactly the same treatment as these microdissected tumors, we see that before surgery, her CA-125, which can be a blood-based marker to tell you that there's some tumor, is very high. After 6 months of chemotherapy, it's quite low, and 12 months, it's still quite low. So she would be in clinic considered a responder, and we would have predicted from our methods that she's a responder. Now, this is the case that has worked the best. We're still working out the kinks. So we started this in 2007. We're now 2017, so it's taken us 10 years to get to the point where we can create these devices, we can get the tissue, we can keep it alive, we don't smash it or crush it at the very beginning. We know what conditions, how we have to give the chemotherapeutics. So our next big focus of research will be to do this hundreds of times over with patients to see if this can outperform biomarkers in telling us which drugs we should give our patients. So just like it takes a village to raise a child, it takes a whole bunch of people in a laboratory to do this type of research. We have to have consent nurses, we have to have people who do the biobanking, we have to have the engineers, we have to have the people who make the MDTs, we have to have the people who run the molecular pathology platform and the students who do the research. So this is just a look at the current crop of people who are doing all this work. I'd like to thank also all the funding organizations and point out that without that funding, we wouldn't have been able to do any of this research. Thank you.
Thank you, Anne-Marie. Our next speaker is a young researcher recruited in 2010 at the Goodman Cancer Research Center. Dr. Luke McCaffrey obtained a PhD in pharmacology from the University of Western Ontario. He obtained a CIHR postdoctoral fellowship to train with Dr. Ian McCara at the University of Virginia. And he was recruited back here in 2010, and now he's associate professor in the Department of Oncology, and he's a member of the Rosalind and Morris Goodman Cancer Research Center. He's won an FRSQ Junior Scholar, and he's the recipient of a Terry Fox New Investigator Award. And he's been looking and investigating a tissue remodeling of epithelial tissues during breast and ovarian cancer initiation and progression. So you're going to hear more about metastasis in his talk. So Luke, welcome to the public forum. Except it doesn't show. That's why we're using.
I'll use the mouse because the laser pointer doesn't show up.
Okay.
So you have the mouse here.
Okay, so it's my pleasure to be here to talk a little bit about the research that we've been conducting in the lab over the past few years, but also I think to highlight some of the basic and fundamental biology that's been going on to understand at a molecular level and a cellular level epithelial ovarian cancer. So this is just an image that we have showing what we're going to talk about is this metastatic phenotype of ovarian cancer and these spheroids of cells that are really these metastatic units that can prolong the disease. So this is just a little overview. I think it's been covered quite nicely, some of the clinical elements of ovarian cancer. So what I'd like to bring is a real a basic or fundamental perspective to this. Okay, so some of the questions that we have are, how does the disease initiate? How does it spread? And how does it evade different therapeutics? And we're really looking at it at the cellular and the molecular level. Okay, and so this is what we bring, and these are the types of questions that we like to ask and that we like to address. And so really I think the fundamental thing that we can bring as basic scientists to this is to understand how the disease works, okay? So it's like if you go to the mechanic, if your car is broken, if they understand what the problem is, they can fix it, okay? So the same thing with diseases, and particularly ovarian cancer. If we understand, really how this disease progresses and initiates, then maybe we can have more success at treating it. Okay, so it's been introduced, epithelial ovarian cancer by Anne-Marie in the last slide. So what we're interested in here is some of the more aggressive and later stages. So when the disease is metastatic, so this is when it's moving to different regions within the body, okay? And so what's known is that fewer than 30% of patients will survive beyond 5 years after diagnosis if they have the metastatic disease, okay? So this is really, I think, a significant problem that continues to exist within ovarian cancer. And so this is really going to be the foundation of what I talk about today, is some work in the field, but also some of our own work at understanding these mechanisms. Let's see what time I started. Okay, so ovarian cancer metastasis really is involves the abdominal cavity, okay? So the whole abdominal cavity within the patient. So I just wanted to overview a little bit here of what we're looking at. So here the abdominal cavity is really this space that occurs in between the organs and the wall of the peritoneum here, okay? And so there's a number of tissues and organs in here that can be sites where these cells can leave the ovary. So Walter had nicely described how, the ovary is the primary home of these ovarian cancer cells, maybe not the origin, but the home that they reside in. But what they can do is they can move to different sites, okay? So they don't stay put within there. Okay, so it's been described that these tumor cells initiate in the ovary, or they grow initially in the ovary, and they can go to different sites. And it's often been described as a process that's been called a passive dissemination. Okay, so the idea that these cells are on the ovary and then they're shedding off and passively moving to other locations. Now, I'm not a big fan of the idea of passive processes within biology. So I think that there must be mechanisms that are that are driving this process, okay? And if there's events and mechanisms that actually drive this process, then maybe there are unique targets that we can determine there to actually block some of the progression and block the metastatic disease. Okay, so as has been described, ovarian cancer, these cells grow and initiate in their home site, the ovary. Okay, and so then what happens, and what's often found in patients with metastatic disease, is that they'll develop ascites. Okay, and so this is really a fluid that accumulates within the abdomen of patients. And so what happens is that the lining of the organs and the abdominal cavity, it secretes a fluid, okay? And this fluid, it's a thin layer of fluid that covers the abdominal cavity. And what happens is that this fluid is normally drained, okay? So there's some produced to help lubricate the tissues, but then it's drained. And so what happens is that the drain gets blocked. So if you have for example, if you're having a shower and your drain is blocked, you find you're up to your knees in water by the time it ends, right? At least I do with 2 daughters. So this is what happens. So the same thing happens within ovarian cancer. There's blockage of the drainage, and you get this accumulation of fluid. Okay? And so what happens is that these cells from the primary site can disseminate, and they can detach from that primary tumor and enter into this acidic fluid. Okay? And so then this acts as a conduit, and this is called malignant ascites. Okay? So now you have this fluid with these malignant cancer cells that are floating around in it. Okay. So if you think about this in terms of movement, okay, so if you were to move from your home into another site, into another home somewhere else, you'd pack up your car, your moving van, and then drive down the road. So really this acidic fluid is like that road, okay? It's connecting the initial site to the future site that it's going to. So the next step happens, these cells are floating around, and then they start to adhere to different organs and different sites within the tissue. Okay, so the moving van has arrived in front of the house. So what has to happen next is that these cells will invade into these tissues, and then they'll start to grow there. Okay, so this is a new site for them to grow. So there's a lot of challenges that actually have to occur because they've evolved their whole life in growing in the ovary, and now they're asked to first survive in the ascites, and then also survive at a secondary site and grow into a secondary tumor. Okay, so there's a number of challenges that these cells undergo and have to overcome to actually survive in these processes. And so one thing, that I'd like to bring up is this a concept that there are these cycles of dissemination, okay? So the ovarian cancer will start to disseminate from the primary site and land in these different tissues and organs within the abdominal cavity, okay? And so the idea is that this can be maintained through this continuous cycle. So once they land in another site, they don't necessarily stay there. They could actually shed from that site as well and continue to shed and reattach to different sites. Okay? And so the question that we have is, what are the mechanisms that can underlie these cells' ability to actually shed from a site, either the primary or secondary site, and reattach at other sites? And can we understand those mechanisms, and can they be blocked with drugs, perhaps? Okay, so the idea here is that after surgery, so the ovaries have been removed, and a lot of the tumor has been removed from within the abdominal cavity through a process called debulking. And then chemotherapy can be used to help clean up some of those other cells that are maybe residing. But what can happen is there can be small populations of cells that have been missed, okay, or are resistant to the current treatment. And so you can see those here. There's a little nodule here and a little one here. So these can act as seeds to sort of reinitiate the tumor, okay? So these resistant populations can come back, okay? And so this is what Anne-Marie was talking about. You can have these other populations that are maybe resistant to certain drugs, and so coming up with personalized medicine to target some of these populations, I think is something that's going to be very important for the future. So you can have this reseeding, and what happens is you get continual reseeding, and it repopulates sites within the abdomen, okay? And so what happens is that the abdomen actually acts as a reservoir for these tumor cells, okay? So it acts as a reservoir, and so if you continue to clean out, if there are cells that are missed, they're just going to keep reinitiating the tumor and maintaining it. Okay, so back to what a malignant ascites is. So about a third of ovarian cancer patients will have ascites at their diagnosis, and almost all of them have ascites at recurrent disease. Okay, so this is a very important process, I think, that's involved in maintaining this disease. And so really what the malignant ascites refers to is the presence of these tumor cells within this fluid. Okay? And so the idea is that these tumor cells can exist as single cells, or more often as these groups of cells. Okay, so it's like a gang of tumor cells that's available. Excuse me. Sorry. Okay, so these multicellular gangs of cells are often referred to as spheroids. Okay, so in addition to cancer cells, there's a number of other cells that are present within the ascites. And so these are things like immune cells and other cells like fat cells or fibroblasts that have come from damaged tissue. So either the ovary or some of the other sites within the abdomen. And these are cells they're shed into this fluid. And what happens is that there's a communication that occurs between the different populations of cells. So these cells down here, they can actually act to help promote and provide factors to promote the growth and survival of the tumor cells, okay? And so really, what the point that we're at is that these groups of cells actually can support each other, okay? And so the idea is that these groups of cells have enhanced growth, survival, resistance to chemotherapeutics, and these are actually the ones that are more capable of invasion and metastasis. Okay, so what happens with these groups of tumor cells as they're going to land on different organs and tissues and start to invade? So there's a natural barrier. So there's a thin layer of cells that covers the peritoneal cavity and different organs. And this cell layer is called the mesothelium. Okay, and so it's a thin layer of cells. And so if we go back to the analogy of moving, so this would be like you show up with your moving van and the house has a fence and there's a locked gate in front of it. And so what do you do? Well, if you're a cancer cell, you just kick down the gate and go through. And so that's what they do. So it's been found in patient samples that underlying the tumor of the malignant cancer cells, there really are these holes in the mesothelial layer. Okay, and so what happens is that the tumor cells will penetrate through there, and then they'll go onto this supportive matrix, and that's where they can kind of anchor themselves and continue to grow. Okay, so the questions we have are, how do they do this? How do the cells actually get through this protective barrier and seed into the lower regions to actually grow? So this is work that was done by another group, not by us, to look at this at the mechanism of attachment of these things. And so what they did is as Anne-Marie had described, these 3D sort of culture systems. So what they've done is they've created a system that has multiple different cell types. So they can create a system where you have a mesothelial layer, shown here in green, and then on top of that, you can put the cancer spheroids, okay? So these are these balls of cancer cells. And so, excuse me, in the bottom panels here, what you can see are just different views of the same thing. So we're now in this panel down here. You're looking from the top down, okay? And so what we can see here in this second row is this is just showing us the cancer spheroids. And what this row here is showing is just the mesothelial layer, and then this is a pseudo-colored overlay of the two, okay? And so what you can see is that at different times when they've added these spheroids to the mesothelial layer, you start to get these holes. And so what you can see here is that you're actually getting this expansion of this hole, okay? So the cells are actually able to penetrate and drive through that. And so if we look mechanistically at how this happens, so what happens at the first step, so the top part in that panel, is that the cells will interact, okay? So they have hands on them, and there's handles on the mesothelial cells. And so what the cancer cells do is they're going to grab on, okay? And they're going to attach onto these cells and grab. So what happens in the second step in the middle there is that they actually start to exert a force, okay? So they'll start pulling, and they're quite aggressive. They exert a force, and they start roughing up that mesothelial layer, okay? And then in the bottom one, what happens is the mesothelial cells are actually stimulated to move away from it, okay? So they don't like the insult. They start to move away, and that's where these cancer spheroids can actually drive through and penetrate down underneath, okay? And then they can set up their roots, and they can establish interactions there to grow. So what's interesting is that if you block the adhesions or block this force that these cancer cells can put on, you can actually block the whole invasive process. So these cells are now no longer able to actually invade in and set up these metastatic lesions at these sites, okay? So this shows that there is, the possibility to understand some of the mechanism that goes on there and then actually block this process, at least in an experimental system, okay? Okay, so one thing we know is that these cancer spheroids seem to be the main drivers or the metastatic units of ovarian cancer. And so one of the questions that we had in our lab is how are these generated? Okay, so how are they actually produced? And so one of the possibilities, and this is the most popular possibility that's been put forward in the literature, is that the cells leave the tumors as single cells and then they aggregate together in ascites. Okay, so the idea is that these cells will lose adhesions with their neighbors. They'll, in bulk start shedding off, and then because of high density of cells within the ascites, they'll actually group together. Okay, so this, if we go back to the analogy of moving, it would be, if I leave my house by myself and I go out onto the street and ask for 5 neighbors that want to move with me. And they say yes. So we all pile in the car and we go live as roommates somewhere, okay? So the problem is if you look at the genetics, so what happens is you can start looking at the different populations of the primary tumor and all of the metastatic sites, okay? You can actually create a family tree for these things, okay? And so you can look at, are they related or are they not related? And so when this is done, it turns out that these tumor cells are actually related to each other. So it's not just aggregation of various tumor cells from around the different, from around the primary tumor, but they're actually ones that have come, that are genetically related. So this made us question, whether this is actually the model where these cells will detach and leave. So we came up with other possibilities. So another one is that the cells could leave as single cells and grow into spheroids. And they just grow themselves into a ball of cells, okay? So the other possibility is that cells actually leave as groups, okay? So I think what you can appreciate here is that there'd be different mechanisms that are involved in each of these type of approaches. So in one, you would have cells that have to leave, lose their adhesion, and then re-adhere. The second one, you'd have to have cells that have a real growth stimulus to actually grow into balls. And the third one, you have to somehow get a mass of cells to leave at once, okay? So this is the question that we had, what's the process here? And if we understand this, are there maybe unique applications for treatment? So the model that we chose and the model that we developed for this was a mouse model. Okay, so the nice thing about the mouse model that we use is that, as Anne-Marie said, you can put human cells into an immunocompromised mouse. And so that's what we did. And so the advantage here is that now we can recreate the whole process. So when we put these cells into the ovaries of mice, they will grow a tumor, the cells will shed, you get ascites, and they'll disseminate and attach to different organs around the body, okay, of the mouse. So it's a really nice model where you can recapitulate a lot of those events. And so what we did is we took the tumor cells and we labeled half of them red and half of them green, and then we put them in their colors into each side of the ovary. And so the idea was that if these cells detach and aggregate in the ascites, then what you would get mixtures of those two cells. So they actually come together and mix in the ascites. And if there was no aggregation, then they would actually be single cells. So this is the experiment. We can see here on the left that it's a pure red tumor, and the right is a pure green, and there's no mixing within the ovary sites. So we collect these spheroids from the ascites. What we can see here is that they're mostly a single color. So there are a few that are double color, but about 80% of them are actually a single color. So this was a bit of a surprise. So there's not a lot of mixing and adhesion of these cells that goes on within the ascites. Okay, if we look at the secondary sites, or the metastatic sites, we can see again that each of these different sites is predominantly a single color. So these really are arising from a single spheroid in the ascites. Okay, so it's kind of reinforces that idea that there's this metastatic unit. Okay, so they're not shedding and aggregating within the lumen. So the question was, are they disseminating at a single cells and growing, or are they disseminating as groups of cells? And so we set up a kind of a parallel experiment. And so this one, instead of, so we labeled the cells with red and green again, and we put them into the ovaries, and this time we mixed the red and green. Okay, so the idea is that if it comes off as a single cell and grows up into a sphere, it's going to be a single color. Okay, because it's coming from just one cell that grows into a population. And so it will maintain the color that they have. Now, if it's coming off as a group of cells, it will actually be multiple colors. Okay? And so we did the experiment, and here are the primary tumors. You can see that they're very mosaic, so they're expressing both red and green. And there's a nice mixture of these two populations of cells. And then when we look at the ascites, we can see that indeed these are multicolored. So it suggests that indeed these do detach as groups of cells. And when we look at the metastases, the secondary sites, again, we can see that these are able to seed these secondary metastases and seed both colors. Sorry. Okay, so one of the questions was, how are they actually detaching? And we want to start to understand more of the mechanism that occurs there. And so what we decided to do was develop some little organoid models, and so Anne-Marie had introduced this idea of these three-dimensional organoids. So they're really these little miniature tumors that we can create in a dish, and then we can put them on the microscope and we can do live imaging. So we can make movies of these things and actually watch them detach, okay? And so it takes 18 to 24 hours or so, and we can start to score these events as they come. And so what you can see in the top panel here is that there's a cell that starts to come off right about here, and it slowly moves out. Then there's this little stalk that appears here, and then the cell detaches. Okay, so in this case, this is a single cell detaching. Okay, now if we look at the bottom panel here, this is going to be a group of cells detached. So you can see there's this long kind of weird projection that comes out, and slowly these cells start to move away. And again, we have this long stalk, so it's kind of like an arm that's holding on this group of cells over here to the main body. So eventually that breaks, and you get these spheres coming off, and they reshape into more of a sphere, into more of a spheroid type of shape. Okay. So the interesting thing was that we find single cells and the collective cells were coming off at about the same proportion. So it's about 50% of the time for each. So if we remember back to the mouse model, we found there that predominantly what we saw was the cells were coming off as groups of cells, or that's the origin of most of those spheroids. And so what we did is we labeled these with a dye that could detect the cells that were dying as we played the movies. And what we found is that most of the single cells, so about 85% of them, actually die immediately after they detach. Whereas the cells that come off collective or groups actually have a survival. So this reinforces that idea that these groups of cells can communicate and support each other and maintain their survival. So the last thing we wanted to do was, or at least the last thing I'll tell you about, was to determine whether we could block some of this detachment. So one of the things that we found in I think most of the cell lines that we've looked at, or maybe all of them, is that the cells will spontaneously detach. So if you put them in a dish, you spontaneously get cells detaching. And so this is a fundamental property, I think, of many ovarian cancer cells, is that they have this ability to shed. So we developed an assay where we could grow these cells, and then we would capture the cells that come off, and then use an assay to determine whether they're alive or dead. And so it just colors them green or red, whether they're alive or dead. And then the idea is that we can treat these with different drugs and determine whether it has any sort of effect. Okay? And so this is just an example of the type of experiment. And so we can see here that in the treated, there's a lot of these cells and these large aggregates of cells that have shed off. We can see that in the green, and then the red is showing us the dead cells. And you can see that under different treatments, you can see different types of patterns that arise. And so we treated with a number of different inhibitors here, and what we can see is that in the untreated, that's scaled at 1, but a number of these inhibitors could actually block or reduce the number of detachment events. Okay? So we were able to block some of these cells from detaching. If we look at their survival, again, we can see that some of these inhibitors are actually able to block the survival of these cells after they detach. Okay? So I think this reinforces the concept that we may be able to develop therapies that can actually block some of these processes of this cycle of detachment and reattachment. Okay? So just in the summary, the clusters of cancer cells are more resistant to chemotherapy, and we think that these are really the metastatic unit that can act as a reservoir for disease and recurrent disease. Okay? So they can detach as single cells or groups of cells, but we think that the groups of cells actually have these survival advantages and enhanced chemo resistance, which maybe enables them to maintain the disease more. And so then finally, again, we showed that at least in experimental models, we can block some of these processes to block the detachment and reattachment events. So the acknowledgement, so most of the work that has been done in our lab, or almost I'd say 95% of it on the ovarian cancer project, has been done by Sarah, a very talented graduate student who I think is actually up there, with some help from Joseph and Christina. Of course, the project wouldn't exist without Patricia Tonen's input. So she's the one that initially got us interested. She really pleaded the case that more basic biology needs to be understood about ovarian cancer. And so she really got us excited and interested in understanding some of these processes. And I'd just like to say that, we're not the only lab that's working on ovarian cancer at the Goodman. In the last couple of years, I think there's been a huge sort of burst of activity. So I'll just very briefly, talk about, some of these other researchers in the practice. So there's Yujiro Yamanaka, who's developing some very nice models for the very early establishment and initiation of the disease. So Thomas Duchenne is looking at some of the factors that can regulate survival of these of tumor cells throughout these different stages of metastasis at the primary site, within the ascites, and then at the secondary site. And David Junker, who's an associate member, his primary appointment's in bioengineering. But he's developing some very nice systems to actually isolate these cells. Okay, so this can be used to monitor patients, but also it's a really valuable research tool to be able to isolate ascites, cells from ascites, to then do further studies on those. And so I guess that's it. So thank you for your attention.
And Luke, you forgot one of our last recruits. Logan Walsh is also studying ovarian cancer. So one of the highlights of the public forums is that you hear the clinicians talk and you hear the scientists talks about what they're doing and what they're interested in, and the successes and the failures and the time it takes. But then at the other end of the spectrum is the patient who is going through this ordeal and hoping that new discoveries and new treatments will be available to make sure that they stay with us as long as possible and maybe eventually have a cure. Tonight we have such a patient. Her name is Ginette Moret. She is a patient of Dr. Gottlieb. She has been battling ovarian cancer for the last 6 years. So she's going to tell the audience about her ordeal and her journey through this. Ginette?
Can we take this away?
Do you still need it open? Can we shut it? There we go.
Push that. Okay, I'm getting organized. Bonsoir, good evening. I think we can relax our brain a little bit because I'm not going to be talking about anything scientific, not really. I'm going to tell you my story, the good and the bad. I'm 63 years old, and I suffer from ovarian cancer, and it's been like that for the past 6 years. In 2001, after going through genetic testing, I learned that I had a genetic mutation called BRCA1. People who carry this mutation are at higher risk of suffering from breast and ovarian cancer for women and breast and prostate cancer for men. Following these tests and knowing that I had an 80% risk of contracting breast cancer, I opted for a preventive bilateral mastectomy that same year. At that time, few people knew about this dangerous mutation, so most of them found my decision more than exaggerated. But I know it saved me from a lot of pain and heartache. Months and years passed by, during which I completely ignored the gynecologist-oncologist's strong recommendation to have my ovaries also removed because of the 50% risk I had of suffering from ovarian cancer. At the time, what was not clear in my mind was that this type of cancer cannot go into remission. It is a deadly cancer. Finally, in 2011, at the age of 57, I decided to go through with the removal of my ovaries. I met with a gynecologist to whom I explained my situation. He insisted on running several tests and told me that he could not see the reason to remove my ovaries since all the tests showed nothing abnormal. In my opinion, any good gynecologist should know that you don't play around with this kind of mutation. But this doctor seemed completely oblivious to this important and vital information. I had to explain, insist, plead with him for him to change his mind and operate. It was an easy and painless intervention. Unfortunately, 2 weeks later, the gynecologist called me to tell me that tumors were discovered in my 2 fallopian tubes. These tumors were smaller than a pinhead. Indeed, it has recently been established that the major form of ovarian cancer starts in the fallopian tubes. I immediately made an appointment with a reputed gynecologist-oncologist who was referred to me by the director of genetic sciences at McGill University, Dr. Walter Gottlieb of the Jewish General Hospital, accepted to take me as a patient, made an aggressive treatment program for me, and promised me that following the treatment and the fact that the tumors were practically microscopic, I would never have to come back to the hospital after that. In June of 2011, I started a series of chemotherapy treatments, which lasted many weeks. Halfway through the treatments, Dr. Gottlieb proceeded with robotic surgery, a state-of-the-art type of intervention in which a robot, directed by Dr. Gottlieb, made a few tiny incisions on my abdomen. When I say tiny, it's tiny, to remove the rest of my reproductive organs. It blew my mind. I thought it was extraordinary. I was operated on a certain day. I spent the night at the nurse's station talking with everybody, and the next morning I was ready to go home without any pain or discomfort. I never took any medication. The week following the operation, I resumed my chemo treatments without any secondary effects at all, apart from losing my hair. Wait. They never really grew back, but that's okay. At the end, Dr. Gottlieb was convinced that if anyone should be cured from ovarian cancer, it should be me, because of the very early diagnosis and the aggressive treatments I received. A year and a half later, I started having persistent lower abdomen pain, like small electric shocks. It's not a normal pain. It's not like having, a belly pain. It's like little electric shocks. I was not sure what was going on. So I waited a few weeks before going to the Hôtel Dieu de Sorel hospital where I was formerly operated on, and where I had been initially, that's what I just said, initially operated. There I underwent a scan, and the technician told me right away to see my oncologist as soon as possible. My lower abdomen was filled with metastasis. I immediately made an appointment with Dr. Gottlieb, who had the surprise of his life when he saw me in his office. After that, there were many series of chemotherapy treatments, followed by periods over which I was free of cancer. My case was discussed by many gynecological oncologists who came to the somber conclusion that ovarian cancer could not be diagnosed early enough to impact outcome, as mine was the size of a pinhead that could not be detected, prevented, nor put into remission, even with the most aggressive treatments, including weekly chemotherapy and surgery. Finally, no detection method, as was told to you beforehand, no detection method known to the medical community can find the cancer early enough to make a difference. This is why ovarian cancer has the sad reputation of being the silent killer. According to the Canadian Cancer Society, this year only, just 1 year, 2,800 new cases of ovarian cancer will be diagnosed in Canada. Of these 2,800 women, 1,800 will die during the same year, which represents a mortality rate of more than 67%. Of the 1,000 women survivors that year, let's say this year, a good portion will die next year, along with the 67% or 68 or 69% of next year. So it goes on and on and on. If we compare this mortality rate to breast cancer, which rate is of 19%, the difference in rate is enormous. As for me, 6 years later, I continue to survive with a sword over my head, hoping that whatever is holding it is strong and sturdy. Presently, I have been following an oral chemo treatment in which I have been taking 12 capsules per day, every day, for the past more than 8 months. This relatively new treatment called Lynparza, which is olaparib capsules, was developed by AstraZeneca pharmaceutical company. This treatment only works, as I understand it, with women who have the BRCA mutation. Other women with ovarian cancer will have to continue with the intravenous chemotherapy, which after each round of treatment will shorten their time without the reappearance of the cancer. As an example, after my first series of intravenous chemotherapy, I was cancer-free for 18 months. After my second series of chemotherapy, I was cancer-free for 12 months. And after my third series of chemotherapy, I was cancer-free for 6 months only. Furthermore, those aggressive treatments have a devastating impact on the body and its immune system, so that many women will die of problems related to the treatments as well as of the cancer. For example, my mother suffered from one breast cancer and later from the other. She had her other breast removed and was treated exactly the same way as the first time with intravenous chemotherapy, which caused a massive infection and killed her. She did not die of cancer per se, but from an infection due to the treatments, and this can be true for all types of cancer. So for women like me who have the BRCA mutation, the Lynparza oral chemo treatment is vital. Unfortunately, the Régie de l'assurance maladie du Québec refuses to pay for this treatment, alleging that chemo treatments, which are already covered, are available to me. I have written to them many times to explain to them that I was at the end of the intravenous chemotherapy road and that I did not have any other choice but to receive the Lynparza treatment if I was to survive long term. Nevertheless, I continue to receive letters of refusal on their part. That is the Régie de l'assurance maladie du Québec, which we pay for heftily. Happily, the AstraZeneca pharmaceutical company has accepted to pay for my treatment, and I am greatly thankful to them. The secondary effects related to this treatment are different from one person to the other. For my part, the effects are mostly fatigue. I've been very lucky since the beginning. I notice that many fundraising campaigns take place for prevention and cure of many types of cancers. As for ovarian cancer, I wish there were more information activities and fundraising campaigns to primarily help women understand the importance of this killer cancer and to also help researchers find a cure for ovarian cancer, which is so devastating to women and which we don't often hear about. Lastly, I want to invite women to examine their risk for ovarian cancer with their doctors, and if the risks are considered important, to act accordingly without hesitation. Thank you.
So I would invite the speakers to come to the front table. There's one more slide. So if you have questions, please write them down on the cue cards. We'll collect them. In the meantime, as you can see on the screen up there, if you want to follow our activities and you want to see exactly what's happening with the public forums, you can follow us on all these platforms. The videotapes will be edited and should be up on our website within the next 2 weeks. And the next public forum is on November 29th, which is a Wednesday. So maybe we'll have snow by then. I know, but it will happen. Okay, so a question for Dr. Gottlieb. If an ultrasound of the uterus clearly states a thickening of the lining of the uterus, does this indicate the start of an ovarian uterine cancer?
No, there are many, many reasons, most of them non-cancerous, for a thickened lining. However, the remote possibility of a cancer absolutely needs to be excluded, because that's the important one that we want to make sure is not there.
For Jeanette, did you have a CA-125 level high enough your journey? So if you can expand on the CA-125?
Well, when you start treatment, first of all, I found out I had the cancer, and then I started treatment with Dr. Gottlieb. They test that the CA-125, which is a marker, I guess we would call it. So you get tested for that every time. So when you're in treatment, it's every week. And when you're visiting, because he never gets rid of me. So every time I see him, I have a CA-125 test. Does that answer the question?
Yes. I have a lot of the cue cards that essentially come up with the same thing.
How did the CA-125 change with the treatment, especially the last treatment?
So does the CA-125 go down on your last?
Oh, yes, yes. The treatment, yes, as you get the treatment, and that's how we find out, that's one way of finding out, is that the CA125 goes lower and lower and lower. Yeah.
What would be the signs that a patient would have that could be indicative that she has to consult immediately?
So let me take the opportunity just to insist on what Jeanette said. So Jeanette had no signs. Jeanette had no CA125. Jeanette just went on to convince her gynecologist, please take out those ovaries. And what was found was something completely microscopic, a few abnormal cells. If anybody, indeed, like she said, if anybody should have been cured, she should have been cured. This completely changed my view of Jeanette's story, completely changed my view of what screening and early detection can do. And I think that her plea that if you are at risk of ovarian cancer, the only thing that really can help you is to remove the organ at risk. And remove it as early as is reasonable, meaning once you finish fertility. Concerning?
So one question here says, what form of testing, for instance,
Okay.
ultrasound, MRI, CT scan, blood test, will detect the beginning?
It won't. Nothing will detect the beginning. You know, by the time you can detect it by any of the means that we have available in 2017, it is already late in its effect. Now, you might detect it before it gives symptoms, because for an ovarian tumor, again, because it's not innervated and because it doesn't affect any of the functions that a normal ovary would do, the time you detect it is when it's so big that it causes symptoms, when it pushes on its vicinity, on the neighbors, pushing on the bladder, pushing on the abdomen, increasing abdominal girth. So the symptoms are really from something that's kind of pushing around there. And most of those symptoms are symptoms that everyone has from time to time. So it's very difficult to make a difference between, you know, it's an indigestion or I just feel a little bit weird today, to ovarian cancer. What makes the difference is really, you know, you have a right, everybody has a right to have a little bit cramping, to have a little bit pain, to have a little bit bloating. But if it persists and it doesn't disappear, that's when the light bulb should go on, and that's when you should be examined.
Actually, two cards that essentially ask the same question. Is the CA125 marker always an indication of ovarian cancer?
The short answer is no. CA125 can be elevated by all kinds of other abnormalities. It's basically a marker of irritation of the peritoneal lining that we heard. So when the peritoneal lining is irritated, you get CA125. A lot of diseases, all kinds of inflammation, infections in the belly will elevate your CA125. Heart disease can do it, cirrhosis can do it. Lots of things can elevate the CA125.
So to pursue this, it cannot be used as an annual test.
Absolutely not. It has it. Yes, yeah. Actually, also. So it is only of value to follow once the cancer is established. It is absolutely not helpful to make a diagnosis because it's elevated for many other reasons. And in 50% of cancer, it won't be elevated. In early cancers, it won't be elevated.
Luke, a question for you. Does cell attachment at the secondary site have a preference for one organ or the other?
So yeah, there is evidence that there is preference for particular organs. So the omentum, which is a fatty organ that hangs from the stomach and covers the intestines, there seems to be a preference for that, as well as the abdominal wall. So there are preferences for sure. I think it's not exactly known what the preference is or what drives that preference, but there is some molecular reason that there is a preference for particular sites.
Genetic transmission. If a mother died of ovarian cancer, is the person in the room at a chance to develop the same disease? Patricia?
We have the expert in the room.
So so the question is, again, if
a mother died of ovarian cancer, am I a candidate for it?
for ovarian cancer, yes. Even without the gene, the risk of developing ovarian cancer for the daughter is 3 times or more higher. If you carry the gene, you have a 50% chance of passing on that gene to your daughter. So it's not 100% of the time. And her chance of developing ovarian cancer is as high as your chance of developing the disease. So it could be as high for BRCA1, if you have a mutation there, it could be as high as 60%. And that the risk is for the course of your life. Okay? There's another gene called BRCA2. And that too increases risk for ovarian cancer, but it's not as high, but it's significantly high in the population. Now, for the population itself, the chance of developing ovarian cancer for any woman in the population, in general, without any knowledge of whether she carries a gene, is about 1%. Okay, so 1 in 100 women, if they live to age 80, could develop ovarian cancer. So in other words, in having inherited a mutation in one of these 2 genes, significantly increases your risk for ovarian cancer. And perhaps had you known that when you were a lot younger, and you convinced your physicians, they could have acted a lot sooner. And by the way, these genes were discovered in 1994 and 1995. So we've known about this for quite some time.
Is that the same for non-BRCA BRCA1, BRCA2? Is it the same ratio for
The risk?
ovarian cancer for mother to daughter?
So there is a risk for developing ovarian cancer that's not what we'd call attributed to being a carrier of BRCA1, BRCA2. So a daughter is definitely at higher risk for developing ovarian cancer if her mother had ovarian cancer, but it's not necessarily based on pardon me?
Is it just as high? Same ratio?
No, it's not the same. And it's hard to predict because sometimes it could be due to genetic factors that we've yet to discover or a combination of other factors.
And Patricia was involved in discovering the BRCA1 and 2.
If I can just add something. We didn't know that we had a mutation before my young sister had breast cancer. And we discovered through the testing that it's my father who was carrying the BRCA1, and he never had cancer in his life. He died in his 80s. So, and my daughter was tested, and she doesn't have it either. Just the sisters and brothers in my immediate family.
So another question for Dr. Gottlieb. You said that the only thing that works in risk reducing is the prophylactic surgery. At which stage do you perform this surgery, and can it be called prophylactic?
So the surgery is advised after fertility is finished, after family planning is finished. And at that point, the longer you wait, the higher the likelihood that you might have something similar to what Jeanette has experienced, which is a microscopic cancer that was discovered at the time of prophylactic surgery. So it's all a question of balance of what is important, what is not important. And for one person, it's going to be more important to finish their family at the age of 35 and have their surgery at 36. Others will have their family until the age of 42 and will want their ovaries out only at the age of 50 when it's closer to menopause. And everybody has to kind of live with their own value systems. So what we usually advise is before the age of 40 and after family planning is finished.
Again, for you, Jeanette mentioned that it's important to discuss risk factors. With whom? If even some gynecologists are misinformed, who do we discuss this with?
There is a big campaign that has started last year throughout Canada, which is called No Woman Left Behind, where the idea is really to inform not only the population, but also gynecologists through big efforts of seminars, and also the practicing family physicians about what are the symptoms, what do they need to look for, and what are the risk factors. So we hope that within the next 2 years in Canada, universal knowledge of this will be present. No woman left behind.
Along the same lines, what is known about preservation or prophylaxis in non-gene carriers?
So that goes a little bit to what Patricia said before. In BRCA1 and BRCA2, which are the two genes that we know the most, we have very clear guidelines. We know other genes are involved, and some of them are being tested, some others not. So it depends a little bit on the family history. If the family history is like the lady said just before, my mom had ovarian cancer, that's really the last thing I want to have in my life. Or my mom and her sister had ovarian cancer, my mom and my sister had, then the risk becomes so high, even if we can't put a finger necessarily on the gene at this point, that preventive surgery is valuable.
Anne-Marie, the comment is that most of you are adamant that the current biomarkers are not effective at detecting early stage of ovarian cancer. Are you not hopeful that research will reveal new genetic ovarian cancer specific markers that are more effective?
So there's two kinds of markers that we're talking about, and we can confuse them. So there are markers that are genetic markers. Those are genes who were born with that put us at risk for having ovarian cancer. And although BRCA1 and BRCA2 have been discussed a lot, we know from the disease and families that there are other genes that are being important. So as we find those, then we can counsel women who have them better in terms of managing their risks of whether they want to have their breast removed or whether they want to have prophylactic surgery. You have to remember, though, that that represents 5 to 10% of all cases. 90% of the cases are what we call sporadic cases. So there's no family history. There might be no gene that you're born with. I call it the cancer lottery. So unfortunately, we all have a ticket in this lottery. And if you're born with a gene that puts you at risk, of course, your chance of winning the lottery are much higher. Doesn't mean you're going to win it, but your chance of winning it is higher. And then things happen throughout our life in the environment. We accumulate mutations, and we can also get cancer even if originally our genes were pristine. So they add up. And we can change our lottery ticket by the way we live our lives. So we know, for example, for lung cancer, if we smoke, at birth we weren't smokers, we might have had one lottery ticket, but because we smoked all our life, we might have changed a 1 in 100 chance for a 1 in 5 chance of winning the cancer lottery. So that's the genetic side. There's an environmental side. The other biomarkers that people are talking about are early detection, and I think you've heard rather convincingly some stories that tell you how early can early be. And so even with a case where it's microscopic disease, where you did everything right, you couldn't find it. So the chance that we find a biomarker for early detection is probably not as important as we find curative therapies Because if we can't prevent the disease, we can't screen for it, our next best hope is curing people of their disease.
Again, for you, Anne-Marie, you mentioned bioengineering relative to other cancers. How much help has it been in general? But I think most of you can talk about this.
About the microfluidics or having bioengineers in it. So actually, it's an increasing trend, I think, in terms of research. I presented the work on ovarian cancer, but we've also done the same type of experiences in prostate cancer. It's a little bit more tricky because the cancers are smaller. Instead of working with a big piece of tissue, we work often with biopsies, but we've shown that it can work. But engineers are helping us do other types of work too. For example, we know that often we don't just find tumors at the site of diagnosis, but we can actually find it in the blood. So these are called circulating tumor cells. And the engineers are helping us find ways that we can purify these rare cancer cells that are in the blood and use them to help us decide on treatment, whether we're responding to treatment. So having those people on board is a lot of help, and the fact that we're starting to bring together bigger teams, multidisciplinary teams, means that our approaches are becoming more and more novel.
Finally, a last question due to time for Dr. Gottlieb. Is there a guideline for automatic referral for fertility preservation before surgery from a young patient?
So fertility preservation has become a very important part of what we do. It needs to always be balanced versus the risk, but in the last 10 years, big efforts have been put in the potential of maintaining that important life event, which is procreation, for at least for those who feel that that is important. And in all patients who are before the age of menopause, we do offer it. Some find it important enough to go through the process. Others, either they have children or they're at this point in their life with the diagnosis of cancer, that's not their focus. But yes, it is offered systematically.
So I would like you to join me in thanking our wonderful speakers. And we are offering you the Goodman Cancer Center cookbook.
Thank you.
So
Thank you, everybody.
Thank you for coming, and we'll see you on November 29th.